Hello students, our next topic is going to be Ampere circuital law. Okay, I have written the statement of it. We'll just read it out first. Before that, I want to tell you what is Ampere circuital law. It is an alternate method. Okay, alternate method to find magnetic field. Okay, we can find the magnetic field with the help of Biot-Savart's law. Okay, similarly, this is an alternate method. It is almost same as the Gaussian method which we have used for electrostatic. In that we were using Coulomb's law, that was basic law. Here Biot-Savart law is our basic law. Similarly, after Coulomb's law we were using Gauss law. Similarly here, after using Biot-Savart law, we can use this Ampere circuital law. Okay, just I will read out the statement. The line integral of magnetic field around any closed circuit or loop is equal to mu 0 times the total current passing through the loop. Okay, if you want to write it in a mathematical form, it is line integral of magnetic field. Line integral of magnetic field. Line integral of magnetic field around a closed loop. Okay, so it is line integral of magnetic field in a closed loop or a circuit is equal to mu 0 times the total current passing through this loop. Mu 0 times the total current passing through this loop. Okay, once again we can see line integral of magnetic field around any closed circuit. Line integral of magnetic field B around any closed circuit is equals to mu 0 times the total current passing through it. Okay, so this is the formula of Ampere circuital law. It is same as I have told you about Gauss law. In Gauss law we were using this thing, E dot ds is equals to Q by epsilon naught, where this was for Gaussian surface and this was electric field. Here it is magnetic field and dl is our current line integral. Okay, I hope this much is very clear to you. Now I want you all to revise something before moving forward. You can go to the previous video and find out what is the answer for this. If there is an infinite wire, okay, then what is the electric field at this point, magnetic field at this point, if this distance is say r. Okay, I'll just revise you. It is mu 0 I upon 2 pi r. Okay, it is this, but still I want you all to revise it, to remember it. I don't want that anyone will take it directly. Okay, just revise the previous video and find out that for an infinite wire at distance r, the magnetic field is mu 0 I upon 2 pi r. If you remember this, then we can go ahead to prove this. Okay, I hope you all have revised it. You can pause the video and go to the previous video also. Okay, so now to prove it, proof. Okay, what we'll do, we'll have a long conducting wire, infinite. Okay, suppose at point we have this, let the distance be r. Okay, then magnetic field at this point will be equal to B equals to mu 0 I upon 2 pi r. Okay, from here can you see that mu 0 is constant, I is constant, 2 pi is constant. It only depends on r. It only depends on r, that is this distance. Suppose I make a loop around it. I make a circular loop around it. Circular loop around it. Then all the points which will have same radius will have same magnetic field. Okay, to show you, I'll just show you a method. Just a second. Okay, here I have taken a bangle and this pen is your current carrying wire. Okay, suppose at this point the magnetic field is mu 0 I upon 2 pi r. Okay, if at this point it is mu, the distance between this is r, here also the distance between the wire and the loop will be r. Here also the distance between the wire and the loop will be r. Because the wire is at the center, at all the points the radius remains same, which means at all the points the magnetic field will be equal to mu 0 I upon 2 pi r. Okay, can you understand that it depends only on radius, and if the radius of this circle is same, then at each and every point the magnetic field will remain same. At each and every point this magnetic field remains same. Okay, I hope you can understand this much. Okay, then we'll move forward. Now here we'll write magnetic field is same at all points on circular loop. Okay, this is our circular loop, and at each and every point the radius remains same. That's why the magnetic field is also same. This curve is known as Ampere's loop. Okay, this point is known as Ampere's loop. Now to evaluate, now let us also find the direction. If this is the direction, this is the direction of current, it will be this way. If I take the direction of current, that is my thumb, and curl it, this will be the direction of magnetic field. Suppose here it will be in the tangential form. Okay, it will be in the tangential form. Okay, this will be the direction of B. Now as I want to evaluate it around the loop, I want to evaluate the magnetic field or the current element on this loop. Then what I can do, I can take a small element dl over here. I'll take a small element dl as I want to evaluate the magnetic field around this loop. So I'll take a small element dl over here. Okay, what will be the direction of dl? Suppose I have a circle. If I want to find, and I take a small element dl over here, what will be its direction? Its direction will be tangential to the circle. At any point the direction of dl will be tangential to circle. Okay, this will be the direction of dl. But here we have also found out that the direction of B is also tangential to this circle, which means that direction of B and direction of dl both are in same direction. Direction of dl is also tangential to the circle, and direction of magnetic field is also tangential to circle. So from here we need to find out, this is dot product of two things, that is B and dl. So from here what we can do, B dot dl, if I want to write it in scalar form, I can write B dl cos theta. Okay, if it would have been a cross product, then it would be, suppose if it would have been B cross dl, then it would be B dl sin theta, as we have seen in Biot-Savart's law. Here it is a dot product, so it will be cos theta. What is the value of theta? As both are in same line, the theta will be equal to 0. So B dl cos 0, which means B dl only, because cos 0 equals to 1. Okay, I hope this much portion is very clear to you. So here what we'll do, we'll take line integral of B dl is equals to mu 0 I. Okay, as B is constant around all the whole circle, B is constant over here, as you have already seen it. So I can remove this B outside. Line integral of dl is equals to mu 0 I. Okay, now what is the line integral of dl? dl is a small part on this circle. If I divide this circle in number of dl parts, okay, then integration of this will be the length of this circle. What is the length of this circle? Length of this circle is nothing but the circumference of the circle. Okay, here I will just write L to show you a simpler form. This can also be your Ampere circuital law, where L is the length of the loop. In this case we are having a circle, so what will be the length? It will be B into 2 pi r is equals to mu 0 I. Okay, now B is equals to, if I take this 2 pi r on the other side, it will be mu 0 I upon 2 pi r. Okay, this is our formula, magnetic field according to Ampere circuital law. Now can you compare this with the magnetic field that we had got due to Biot-Savart's law? both the thing are same, mu 0 I upon twice pi r, mu 0 I upon twice pi r, which means that this law is correct. Okay, I hope you all have got it. You all would have understood it. I want you all to study this theory and keep studying. Stay safe. Have a nice day. Thank you, students.